In mid-2026, the strategic landscape shifted with the observation of new Chinese submarine designs. Satellite imagery from June 2026 revealed a massive, approximately 120-meter mystery hull at the Jiangnan Shipyard in Shanghai. This vessel is particularly notable because it completely lacks a traditional sail structure. Removing the sail cuts form drag and delays flow separation across the hull. Ultimately, a cleaner upper hull reduces the submarine's sonar cross-section, since there are fewer vertical surfaces to reflect incoming pulses. The elimination of this massive structure represents a fundamental departure from traditional submarine hydrodynamics. By removing the sail, the submarine significantly lowers its drag coefficient, especially at tactical transit speeds. It also eliminates the interaction noise between the sail boundary layer and the hull, which is a signature often exploited by adversaries' sonar processing algorithms. This smooth, teardrop-shaped hull essentially removes the corner reflector effect, making the vessel's sonar cross-section resemble an ideal cylinder. As a result, the acoustic target strength is meaningfully reduced, shrinking the detection ranges for active sonars operating in the region. The architectural transition toward a sailless hull design represents a significant evolution in submarine hydrodynamics, though it requires precise technical qualification. While modern naval design discourse frequently employs the term sailless, this description should not be interpreted as the total absence of any superstructure. In engineering practice, these vessels typically retain a minimal fairing or a highly low-profile housing to accommodate essential retractable systems. Asserting that such a vessel completely lacks a sail structure is technically misleading, as even the most advanced designs must incorporate dedicated fairing sections to house critical periscopes, electronic warfare masts, and communication arrays that are necessary for operational functionality. These low-profile fairings are engineered specifically to maintain the vessel's hydrodynamic continuity, while ensuring that vital sensor apertures remain viable for mission requirements. Consequently, the shift toward this design philosophy is better characterized as a deliberate reduction in sail volume and structural drag, rather than an absolute elimination of all external mast housing architecture. Open-source imagery suggests that recent Chinese submarine designs heavily utilize X-form rudders. The Type-095 and the mystery Jiangnan hull both appear to feature this pronounced X-tail configuration. Naval analysts note that an X-tail provides advantages for maneuverability, hydrodynamic efficiency, and safety compared to a traditional cruciform tail. Furthermore, this configuration provides redundant control authority, which is particularly beneficial when operating in the complex bathymetry of littoral waters. While it is theoretically plausible that this geometry smooths the overall wake and actively suppresses flow-induced noise, specific acoustic measurements and fluid dynamic interactions remain highly classified and cannot be definitively confirmed through open sources. The propulsion mechanisms driving these new vessels reflect a gradual convergence in acoustic quieting technology. While the U.S. Virginia and Columbia classes have long utilized mature, shrouded pump jets, open-source analysis indicates that the Type-095 is adopting similar propulsor architectures. Although unverified rumors occasionally suggest more experimental rim-driven systems, the majority of professional analysts assess that these vessels likely utilize a conventional, highly refined shrouded pump jet. Notably, Chinese research institutions have recently claimed that new dynamic sealants and clearance-free pump jet designs can reduce vibration by a factor of 10 to 35 compared to older designs. However, it is crucial to recognize that these figures represent laboratory stage testing rather than confirmed operational realities at sea. Modern submarine stealth relies heavily on exterior hull treatments, an area where all major navies are constantly innovating. Both the United States and China are known to be continuously upgrading their external acoustic coatings to improve broadband dampening capabilities. While optical satellite imagery physically lacks the resolution to determine the exact thickness or material composition of the anechoic tiles on the massive Jiangnan hull, the general trajectory of Chinese naval engineering suggests the integration of more sophisticated acoustic dampening materials. Some university-level research within China has discussed advanced concepts like microsphere-embedded polymers and active magnetostrictive tiles. Yet, available evidence does not conclusively establish that these highly experimental technologies have been fielded on operational submarine fleets. The substantial size of the new 120-meter Chinese hull heavily suggests the integration of a full-scale pressurized water reactor. Given its estimated dimensions, a traditional naval nuclear power plant would provide the practically unlimited endurance and massive power density required for true blue water operations. While there has been considerable debate regarding smaller, scaled-up nuclear air-independent propulsion systems for other classes, such as the Type-095, applying this hybrid concept to a hull of this magnitude is highly unlikely. A full-scale nuclear reactor remains the most technically sound explanation for a vessel of this size, ensuring it possesses the high-speed transit capabilities and operational endurance necessary for sustained power projection. The undersea competition is deeply influenced by the physical sensor apertures mounted to the exterior of the submarines. The U.S. Virginia-class utilizes highly advanced open architecture sonar suites, including the lightweight wide aperture array, providing exceptional passive acoustic detection. Meanwhile, analysts assess that newer Chinese submarines like the Type-095 likely feature extensive conformal flank arrays and modernized low-frequency towed arrays. The reduced sail profile of newer hulls could theoretically provide additional uninterrupted surface area for these acoustic sensors. Nevertheless, the United States is still widely considered to maintain a decisive, historically entrenched edge in towed array technology and overall deep water acoustic fidelity. Raw acoustic data collected by external arrays requires massive computational power to translate into actionable targeting information. The U.S. Navy relies on mature, highly integrated processing backends that utilize advanced hardware to perform real-time adaptive beamforming and target classification. Conversely, China has heavily prioritized the integration of machine learning algorithms to enhance their acoustic classification systems. In the broader strategic theater, open-source inference suggests China is actively expanding its fixed underwater surveillance networks utilizing seabed sensor arrays connected via optical fiber. While the exact operational readiness and integration of these networks remain difficult to verify, they represent a logical, networked approach to compensating for any individual acoustic shortfalls. The acoustic environment of shallow littoral zones, particularly the South China Sea, fundamentally alters submarine detection dynamics. These waters are characterized by high reverberation, variable sound velocity profiles, and intense ambient shipping noise. In these complex environments, raw acoustic quieting is often less decisive than local hydrographic knowledge. Chinese submarine forces benefit significantly from bathymetric familiarity, localized seabed infrastructure, and the protective umbrella of shore-based aviation. Operating within their own geographic backyard allows these vessels to exploit favorable acoustic propagation pathways, narrowing the tactical advantages typically held by deep-water Blue Navy hunters. Perhaps the most critical shift in the undersea balance lies not in acoustic stealth, but in raw industrial manufacturing capacity. China has successfully leveraged its massive commercial shipbuilding dominance to surge its naval production capabilities. Analysts estimate that Chinese shipyards, particularly the expanded facilities at Bohai, now possess the capacity to produce approximately 3 to 4 nuclear attack and ballistic missile submarines annually. In stark contrast, the Western Defense Industrial Base is currently struggling with severe structural bottlenecks. Documented real-world production rates indicate that American shipyards are currently sustaining an output of roughly 1.2 Virginia-class submarines per year, highlighting a profound and widening asymmetry in industrial throughput. Based on available evidence, absolute acoustic parity has likely not yet been achieved across all operational environments, but the historical U.S. undersea advantage is experiencing a gradual erosion. The U.S. Navy retains qualitative superiority in reactor acoustic isolation, deep water sonar processing, and overall operational experience. However, China's new hydrodynamic innovations and expanded production capabilities have drastically altered the tactical calculus within the first island chain. Looking toward the end of the decade, the measurable disparity in industrial throughput will fundamentally reshape the Pacific theater. As the numerical gap widens, securing the contested undersea domain will increasingly require distributed maritime operations and the integration of highly advanced allied acoustic networks rather than relying solely on individual platform superiority.